All right, so now that we can reliably feed the needles, we need to make sure they end up centered. This one actually did a pretty good job. That one's not terrible. That one's starting to overlap a little bit. So you can see, if I could just keep it somewhat centered here, I think that would be great. That one overlapped the edge here. So what I'm going to start with is just a plain old fence going up vertically here. And we'll start there and see if that's enough. Every once in a while they land like this or like this, and that's not great. So we'll see what we can do to improve that, because the robot arm needs to know that they're going to be where it thinks they are. See, like that one there? That was a screw up right there. That's out by a fair amount. So we need to do better than that. First step, I'm just going to drill the chutes to have some mounting holes, some 832s. So these fences have to meet up with the 20-degree angle of the side, you know, because the chutes are at 20 degrees. So I need to relieve the back end of these to 20 degrees. And so I've got a 20-degree block in here, and kind of got these guys flush. Now they're tight. The rear ends of them are matched up against this block here, and I've got them good and tight in the vise. And we're just going to nibble off the side until we get there. Once it's flush with the top, we're good. Okay. I think we're good. So is this sharp? Maybe a tiny bit more. Perfect. Alrighty, I'm going to deburr these, and I just got to drill through holes for the screw mounts, the mounting locations. So I'm on round 2 of these pieces, and I need to drill a through hole here, just in case. I'm going to pull that parallel back a little bit. This is stainless. This is much harder to drill. Feels like we might need to slow this down a little bit. I guess I resharpened this drill reasonably well. This is the one I used on that spring steel that dulled it up so badly. Whew. Nasty stuff. So the first pair of fences I made were perfect at the height they were at the base height here, but when you raise them up, they're too short, as you can see. That's because I calculated this distance based on here to here and didn't think about the fact that they need to be longer when they slid up. So, of course, had to make another set. Let me put these on. Now the question is, will the needles stick? That's good. That's good. Hey, so they're all within about 1/10 of an inch of each other. All right, well, I think that's good. They don't do well when there's more than one down here, but it was only meant to catch one at a time. So we're good. One catches every time. All right. That gives it within 1/10 of an inch, and I think we can handle that. All right, moving on. Okay, so now that we think we've gotten most of the mechanical issues sorted out, we need to do the electronic part of it. And the electronic part of it's not terribly complicated. It could be as simple as having the robot or cobot control the 2 motors individually, but I don't want to waste resources on the robot's controller. So instead, we're going to make it so the robot simply sends a pulse, and this motor will run for 4.5 seconds, and then this one will run for 1 second and dispense a needle. And that's what we're going to do. So to realize the solution where I offload some of the control onto separate devices rather than the robot itself or the cobot, it's going to necessitate the use of these devices over here. If I hadn't, I would have used something like this. And this is a solid state relay. And basically it takes a DC trigger and supports up to 220 volts DC on the output, something like 20 amps. They make all kinds of varieties. So if you're looking for a solid state relay, and the beauty of solid state relay is, one, the contacts don't wear out. It can take really low current, wide voltage range for control of the device, and they control really large outputs. And the contacts don't arc over because it's solid state. That's a really big plus, especially if you're controlling something like a motor, but you just got to be careful that you don't exceed the capacity of the unit. These have the ability to be controlled by DC or AC and have an output that can be, switching DC or AC. Also, you have to make sure to read the instructions. Like this one says that this needs to be on the low side so that when this closes, it's closing to ground. Otherwise, it may not function properly. So you got to be careful about that. But we're not going to go with this solution because this would still require the cobot to turn on both motor individually, and then I need 2 of these, and we're not going to go with that solution. Instead, we're going to go with the time delay relay solution. I chose these 2. I bought a few of them, and all of these would work. This one has a LED display, which is pretty nice. Don't need the fancy display on it. They all work with a bunch of different modes, which is handy. Here's one completely without a display, but the price difference between this one and the prettiest one, this has just got a standard LED display, a 7-segment LED display. This guy has no display, uses a pot to adjust the time delay, and that's a problem because it's very, very sensitive if you want small amounts of time. It goes up to 120 seconds, and I want this to actually be, running in the 1 second and 5 second kind of range. So it's pretty hard to get this pot to adjust. So that sort of ruled this one out. The fancy one is only slightly more expensive, like $4 or $5 more. I think this was like $15 or $14, not very expensive. And I decided on the $12 version just because this would be adequate and does everything I need. It has a bunch of different modes of operation, so I should just cover some of those so you get an idea of what these time delay relays can do. So there's a bunch of different modes these time delay relays work in, and you can read the sheets. They vary between model, but they have a lot of similar versions. So the first one is the one that's going to control the rotary actuator. And what this one is going to do is it's going to receive a signal, the same signal that both of them receive simultaneously from the cobot. When it receives the signal, it will wait 5 seconds, turn on for 1 second, then turn off. And that'll cause the rotary actuator to eject the needle. But before it does that, while it's waiting 5 seconds, this one will basically receive a signal, turn on for 5 seconds, and then turn off. And this will be the agitator. So this will agitate for 5 seconds to make sure the needles are all settled. And then after the 5 seconds, this one will turn on and eject the needle. And we should get a perfect needle ejection every time. I'll be adding a diode on the output of these relays just to prevent arcing from inductive kickback, because motors and rotary actuators are essentially giant inductors. And when they turn off, they resist the breakdown of the magnetic field by putting a reverse polarity current in the circuit, and that can cause arc over on relay contacts and wear them out. So these diodes will just extend the life of the relay contacts. They'll be in reverse, so they only conduct when the voltage is coming backwards, current comes backwards, which is what you want. So we'll be putting these 2 time delay relays inside this box to protect them, and it'll be powered by this 24 volt throwdown adapter. It's a switching converter, 24 volts at 5 amps, very convenient. And the circuit is right here, and I'll go over how the whole thing's going to work. So the cobot has a general purpose output. Actually, it has a bunch of them. And one of those outputs will provide 24 volts when they want it to be active. So the cobot says, okay, I need to go get another needle. Send me put 24 volts on the positive of this relative to this negative here. And both of the time delay relays will receive that signal simultaneously because they're in parallel. The one time delay relay will start a 5-second countdown and then be on for a second, and that's the rotary actuator. The other time delay relay will run for 5 seconds on, and that will be the agitator. So basically the agitator will be on for 5 seconds. This will wait for 5 seconds and then run the rotary actuator to eject the needle. And the output of these, they have the normally open, common, and normally closed contacts. We're going to use the normally open and common so that when the relay engages, this will close. You will get a voltage on the output. There is the diode across the motor in reverse polarity to protect it, because the positive is attached to common, so this will become positive here. That's reverse bias diode. It'll power the motor. When the relay contacts open, this inductor will be charged with a magnetic field. As that field breaks down, it'll try and run current in the opposite direction, so this will become negative instead of positive, and it'll just short to itself through the diode and not arc across the contacts of the relay. And we have one of those on each one. And that's pretty much it. Very simple circuit, and that's what we're going to wire next. One more feature of these guys is while you're trying to program them, they have a micro USB connector, so they're powered between 3 and 30 volts, but you can just plug a micro USB from one of your old cell phone chargers into this guy and program it before you put it in the circuit in case you haven't got everything else wired. Pretty handy, huh? This project box I've got here has a bunch of different options for mounting PC boards. Unfortunately, I can't use most of them, so it has multiple screw holes. If you had a PC board, if you were laying one out, you could lay it out to fit in here perfectly. That can just screw right in without needing your own standoffs. Can't quite use that. It can hold some PC boards vertically if they're small enough, 4 of them, and it'll be captured by top and bottom. That's another nice feature. Can't use that one either. But I might use one of these standoffs and then make another standoff, or find another standoff that fits there, and I can just mount the 2 circuit boards there. Although I don't know if these will fit this way. I would kind of like them. Look at that. Talk about just not quite fitting. I would like them like that, because that sets the wires in and out more conveniently. So because we want to get access to the wires and things aren't quite oriented right for this guy, we are going to mount these in the top of the case. Yeah, it doesn't go perfectly any direction, so we're going to still go this way, and we're going to mount these in the top of the case. Fortunately, these holes are perfect to tap 440. This is a spiral flute tap. And of course, like typical plastic, cuts like butter. Got 1 screw in each side. Just going to mark positions for the opposite screw holes where the standoff's going to go. If you haven't soldered and tinned a wire before, the trick is to get a little bit of solder on the tip of the iron so it conducts heat properly. Then put the solder on one side and the iron on the other side, so the solder has to flow through the wire. And then you'll end up with a perfect tin job every time. So to help do layout with calipers on the plastic so I don't have to score and damage the plastic, I've put some of this aluminum air conditioning tape on it. Lets you make very visible scoring lines without damaging the underlying plastic. So I want the depth to be consistent, and I got to figure out my spacing from the sides. How about 1 inch? So there, and I want it there, and there, and there. See, very easy. Makes easy to see marks, and it won't damage underlying plastic. These are going to be the entrance / exit points for the power in, trigger in, to motor control out. I'm going to put it on the opposite side from this guy, and it's going to sort of, the wires will be open like this so you can work on it, and then fold over with all the excess wires being buried up here. It seems like that'll work fine. The aluminum tape also gives you a tiny bit of protection in case things walk a little bit. Not a lot, but a little. But you can end up getting some nicely clean holes. On some of these, the drill bit just sucked into it. I pre-drilled with a smaller hole size, 1/8 inch, and then went for the 5/16. And this is where the grommets are all going to fit. Grommets are little 2-sided rubber things, in case you didn't know, that have a hole in the center. They let you run a wire through so that the wire won't get cut by the plastic or metal, whatever you're going through. So once I pressed it in, the little ones were too small for the power wire, so I went to the next size, grommet up. Fortunately, a set like this on Amazon or other places was very inexpensive. It's got a bunch of different sizes. And if you go too large a size, there's always an easy solution to keep the wire in place. And all you have to do, this one actually is a good fit now that it's reduced, but all you have to do to keep the wire in place is just put a tie wrap on the inside. And then it prevents it from pulling out. You don't care so much if it goes in typically, but you know, when you're worried about it pulling out and breaking a wire, one of the small ends, then that's the solution you use. Let me give you a hint for a little tip. For anyone that works in the industry, you wanted to find one pet peeve that gets most people really upset. If you don't cut a tie wrap off flush, so you can either use the tie wrap tensioning tool that'll pre-cut, or get some flush cutter. These aren't even flush cutter, but they're micro bevel dikes. And if you don't cut and remove the tail on this, when you reach into a piece of equipment, these things are little razors. If you cut them at an angle like this and leave that thing sticking out, I can't tell you how many times I've gotten cut up by reaching into a rack of equipment and have a tie wrap get me. Very, very common, unfortunately. So if you want to keep it on both sides, you can just put, you know, keep it from moving at all. You can just put a tie wrap on each side. I don't know that that's going to be a problem with this, so I'm not going to put on the outside for now. But yeah, that generally solves the problem. So these two guys I also can put tie wraps on so that they won't pull out too far. To get the outside insulation off the wire, I use a trick where you run a razor blade around it and don't score all the way through, and then just stretch it to have it come off. Now this is twisted wire inside here, so it's a little challenging to get off of the other two wires, but definitely doable. Alrighty, so I dressed the wires up a little bit. This will keep this out of the way of the center. Once we set these, it's going to be set and forget, so that shouldn't be a problem. I could have run some wires down and around, but I didn't want to try and bury all that excess wire. This is going to be a clamshell design, so this just needs to fold in and none of the wires get stuck on this lip where they get cut. That seems to work pretty well. So I'm happy with that. None of these are sharp, although I didn't tighten this one enough, so this one's self-loosening, it looks like. Yep. All right, so over here at the motor side, I've got two motors. I've preset these 50-50, gonna get it 100% wrong almost certainly, but that's okay. That's just how it works out. I'm gonna have to work out some sort of strain relief solution for these guys. This is the motor side. I wanted to put the diodes over here to get them close to the motor. So I got the diode on here, and I'm just gonna put some heat shrink to sort of isolate the diode there, and then fold this wire that's insulated with Teflon tubing around the outside, and then connect that to the black, and then I'll solder onto these both. All right, so here we go. I've got a needle out. I'm going to pop it back in. There's 7 in there right now. Hopefully you can watch it count down. So the bottom one counts down 5, and then the top one ejects a needle for 1 second, which I wish I could do a fraction of a second, but when you're in the mode where it waits a delay and then goes closed for a delay, it only allows full second. So the rotary actuator doesn't need a full second to actuate. Actually, it's much less than that, but I've done this a bunch of times. Works great. So all I've got to do is dress in the wires a little bit so they won't run into anything, and we should be good to go. I cleaned up the wires, added some strain relief in several spots so that we didn't worry about yanking the wires out. The controllers, the time delay relays are inside this box. You can't actually see what's going on, but that's not a big deal. You don't need to see that. The trigger wire is right here. I didn't drill any mounting holes in this plate because I don't know really what it's going on yet, so we can do that after. But this guy is all set to go. This is kind of exciting. We've kind of reached the end of this epic journey, and I'm very excited about that. Here we are close to the end, and we've finished this stage of the process. This part is done, but it's not the complete project, so I won't be able to show you the robot picking up the needles and the laser welding them, because I still need to make a place for the needles to go, and this has to be mounted. So there's a few more bits to do, but this was the main complication of the whole project, and it is now done. So very excited there, and I will definitely send you videos of the next part when I get them. Thanks for watching. Hope you find it useful. Hope to see you next time.